Hello, today I'm going to explain Vesper Theory, or in other words, valence shell electron pair repulsion theory. So we know that they're molecules with central atoms and some other atoms surrounding them. This theory was designed to see what positions these atoms within the molecule will assume relative to one another. Essentially, the theory can be explained in the following way. The central atom has two types of electrons around it. There are shared pairs of electrons, since they're shared between these two atoms, and then there are lone pairs of electrons not inside a covalent bond. Both the shared pair of electrons within the bond and the lone pair of electrons are called electron domains because both are groups of electrons. Also, in order to understand this theory, you have to see that since negative charges repel each other, and since electrons are negative, then electrons also repel each other. Also, you have to see the electron pairs as a single unit of negative charge. So here the bonded electron pair counts as if it was a single unit of negative charge, although there are two electrons present here. And the lone pair also counts as a single unit of negative charge. We call this unit of negative charge, or this pair of electrons, an electron domain, no matter whether it is in a bonded pair of electrons or a lone pair of electrons. It is still an electron domain. Furthermore, we will ignore any repulsion that these pairs of electrons have within themselves. So here's one electron, here's another electron, we would expect them to repel, but for the case of Vesper theory, we will count this pair of electrons as a single unit and ignore repulsion in between the pair. Because each of these electron domains counts as a negatively charged unit, an electron domain, they repel each other. So that's why this electron domain, is on one side of this central atom, and this electron domain is on the other side of this central atom, because these negatively charged electron domains repel each other. Therefore, for the rest of this video, I will be referring to the bonded pair of electrons, the shared pair of electrons, as a single dash drawn here in between the central atom and the peripheral atom. And this outside lone pair will be drawn as a lone pair around the central atom. So Vesper theory, as we have previously mentioned, deals with the varying arrangements of atoms around the central atom. These varying arrangements between atoms are caused due to repulsions between various electron domains around the central atom. For example, if we take a central atom with two shared pairs of electrons, each bonding to an outside atom, the domains with these shared pair of electrons repel each other. And that is why we do not see this shape, but instead this shape, because this domain repels this domain, so that this domain and this domain are on opposite sides of this molecule at an exactly 180 degrees across from each other. Another example, if we were to take a central atom with three bonding electron domains around it, the electron domains would not be clustered up like in this molecule. Instead, they would spread out to a maximal distance from each other, like in this molecule, due to the repulsion between each electron domain of shared pairs of electrons. When discussing molecular shapes in Vesper theory, we'll be referring to two types of shapes. The first type of shape is molecular geometry. This refers to the position of bonded electron pairs relative to one another along with the atoms they are bonding together. In this case, we ignore the lone pair of electrons and just focus on these bonded pairs of electrons, these bonded electron domains, and their positions relative to one another. The second type of shape is the electron domain geometry. This shape refers to the position of both bonded pairs and lone pairs relative to one another in a molecule, since both are types of electron domains. Remember, the lone pair of electrons and the shared pair of electrons are both types of electron domains. In this particular molecule, the molecular geometry will be a bent shape because we're only looking at these two atoms around it and their bonded pairs of electrons, not this lone pair. So that's why it has a bent shape. But in the electron domain geometry, we also take into account this lone pair of electrons here. So when we look at this bonded pair of electrons, this bonded pair of electrons, and this lone pair of electrons, we get this trigonal planar shape because it represents a molecule with 1, 2, and 3 domains sticking out in a trigonal, like a triangle-like shape. Now let's see how we can memorize all of the shapes in Vesper Theory. Here's a helpful chart to follow. In order to memorize the different Vesper structures, you need to know two things. First, you need to know the total number of electron domains. So in this case, there are 2 electron domains. In this case, there are 1, 2, 3 electron domains. And here there are also 1, 2, 3 electron domains. And here there are 4 electron domains. And here there are 1, 2, 3, 4 electron domains. And here there are 1, 2, 3, 4, 5 electron domains. And also you need to know the number of bonded pair domains. So let's say here we have 1, 2, 3 electron domains, but we only have 1, 2 bonded electron domains. For every number of electron domains, there is a distinct electron domain configuration that remains the same with this number. For example, we have 1, 2, 3 electron domains. That means that the electron domain configuration will always be, in this case, trigonal planar. So here, although the bent shape refers to the molecular electron configuration, the electron domain configuration will also be trigonal planar. However, unlike the electron domain shape, the molecular shape changes based on the number of bonded electron pairs. For example, if there were 4 bonded electron domains, then we would get this tetrahedral shape. However, if there were 3 bonded electron domains, then we would get this trigonal pyramidal shape. In order to know a Vesper shape and how it would actually look like, we have to know the number of electron domains and the number of bonded domains. For example, in this case we have 1, 2, 3, 4 electron domains, but we only have 1, 2, 3 bonded domains. So this shape would be trigonal pyramidal shape. In this case, we also have 1, 2, 3, 4 electron domains, like here, 1, 2, 3, 4 electron domains. But unlike here, we have 1, 2 bonded electron domains, not 1, 2, 3 bonded electron domains. This means that this shape would have a bent molecular shape, not a trigonal pyramidal shape. In order to memorize these shapes, we have to see the pattern that develops within each number of electron domains. Within each number of electron domains, we can see that the shapes change as a bonded electron domain is removed and instead replaced with an unbonded electron domain. So here we have for example, a bonded domain, and this bonded domain is replaced with this unbonded domain. And then this bonded domain is replaced with another unbonded domain. So the shape changes as each bonded domain gets replaced with an unbonded domain. For example, in shape 1, all electron domains are bonded pairs. So you do not see any unbonded electron domains. But in shape 2, one of the electron domains is a lone pair. That means one of these bonded electron domains got replaced with an unbonded electron domain. A bonded electron domain got replaced with an unbonded electron domain, and so on and so forth for each shape. And in shape 3, we have two of the electron domains that are lone pairs. So that means another bonded electron domain got replaced with an unbonded electron domain. So now we have two instead of one. And so it progresses. For example, here we have 0 unbonded electron domains. Now we have one unbonded electron domain. Now we have two unbonded electron domains. And now we have 1, 2, 3 unbonded electron domains. Also, within this pattern of adding these unbonded electron domains, we see that they're added to a precise position on this shape. For example, this was a bonded electron domain, and now it is replaced with an unbonded electron domain. However, this unbonded electron domain, the very first one, is not added to here. It's not added to the vertical part of the molecule. Instead, it is added to the horizontal part of the molecule. And so on here. It's not added to this one. It could have been here. Instead, there could have been a bonded electron domain here. Instead, we add it to the side. And here also. Therefore, it is very important to memorize for each number of electron domains where the unbonded electron domains are added onto the molecule, and then you can see how the shapes form. For example, in this case, we add the first unbonded electron domain to the top of the molecule and replace this bonded electron domain. And therefore we get a trigonal pyramidal shape, because it's like this pyramid. It's like this pyramid of a molecule. It's like these Egyptian pyramids. And then we add next unbonded electron domain to one of these side bonded electron domains. We replace it, and now we get this bent shape. Here, for example, we do not add it vertically. We do not add the unbonded electron domain to this spot. Instead, we add it to the side spot, and we get this seesaw shape. And then we add it to another of these side atoms and replace it with this unbonded electron domain. And we get this T shape, because if you flip it like this, it looks like a T. And then the next unbonded electron domain is added to one more side right here. So now we get this linear shape, linear configuration. Furthermore, for this octahedral shape, we do not call it octahedral because it has 6 electrons around it. 1, 2, 3, 4, 5, 6. Because octa means 8. It's because if we attach faces, these faces in between this 1, 2, 3, 4, 5, 6 electrons, we get this octahedron, which has 8 faces. 1, 2, 3, 4, 5, 6, 7, 8. For the octahedral structure, we remove the electron domain right here. So we remove the bonded electron domain and replace it with the unbonded electron domain on one of these bonded electron domains, and we get this square pyramidal shape. Why is it called square pyramidal? Is because if we put a face right here, we put another face right here, and we put a face right here, it begins to resemble this square pyramid. And lastly, we then add the next unbonded electron domain on the opposite side of the original bonded electron domain. So, for example, right here, we replaced it with an unbonded electron domain. And then we add an unbonded electron domain to the opposite side. So now we have them on opposite sides. And we get this shape, it's called square planar shape. Square planar shape. Why is it called planar? Because the square is basically flat. It's on the same plane. It's flat. So in order to memorize these shapes, you have to memorize the distinct shapes for each number of electron domains. So for 2 electron domains, you get a linear shape. For 3, you get a trigonal planar shape. For 4, you get a tetrahedral shape. For 5, you get a trigonal bipyramidal shape. Kind of a tough name. For 6, you get an octahedral shape. And then from then on, you sort of go on and you take these bonded electron domains and replace them with unbonded electron domains to get these new shapes. And that's when you have to memorize these new shapes. But you can sort of see where they come from and don't have to work your mind onto how they form. Just memorize how they form based on each bonded electron domain being replaced with the unbonded electron domain in a certain place on this molecule. And that's how you memorize all of these Vesper shapes. You can also obtain these Vesper shapes from drawing Lewis structures. For example, for the molecule XeF4, we have the following Lewis structure. We have 1, 2, 3, 4 pairs of bonded electrons and 1, 2 pairs of unbonded lone pairs of electrons. However, we have 1, 2, 3, 4, 5, 6 electron domains. So in order to find the shape, the Vesper shape of this molecule, we first draw the Lewis structure, and then we go and look in our Vesper shape table. And later you will have to memorize this by memory for any test you're taking. So in this table, we see that the only molecule with 6 electron domains corresponds to this octahedral shape, the square pyramidal shape, or the square planar shape. Because 1, 2, 3, 4, 5, 6 electron domains is also 1, 2, 3, 4, 5, 6 electron domains here. However, this shape, the octahedral shape, and this molecule shape are not the same. Because in this molecule, we have 1, 2 lone pairs of electrons. And in this molecule, we do not have any lone pairs of electrons. They're only bonded pairs of electrons, bonded electron domains. Therefore, the only molecule here with 2 lone pairs of electrons and 1, 2, 3, 4, 5, 6 electron domains is the square planar shape because it has 1, 2 lone pairs of electrons and 1, 2, 3, 4 bonded electron domains. And that is how you get the Vesper shape from the Lewis structure of the molecule. In the next video, I will work through 5 examples of getting the Vesper shape from the Lewis structure so that you guys can get a good idea of how to solve Vesper theory problems.